Hello, welcome back. Today I'm really excited to introduce a volume of revolutions about slant lines. Yeah, that's right, slant lines. Most calculus settings or teachers won't even talk about this. They usually go over horizontal lines, let's say maybe x equals 5, y equals 5, but they're always straight lines. But they've never introduced revolutions over slant lines. Well, to start this, first let's see what the typical situation is. Well, we're given a function, let's say from intervals a to b, and then we're told, alright, revolve this, let's say, around the x-axis. Fine, you know how to do that. Perhaps around the y-axis. That's also possible. Maybe they get a little bit creative and they say, okay, how about around the x equals 1, negative 1 axis. Okay, it gets a little bit more complicated and so on, but it's all possible, and it's all been covered before. But have they ever talked about revolving a function over a slant line? For example, here we have function f of x, and here we have some slant line, which you know will be y equals mx plus b. Now, what happens if I revolve this around the slant line? Well, visually, it's not that hard to understand. Our area of interest is right here. And if we revolve it around, I would get, let's say, an exact estimate here. It'll look something like this. Something like that. Of course, three-dimensional. It'll look like an oblated cylinder, I might say. Well, conceptually, we can understand this, but now my question is, how would you find the volume? Well, let's understand this in a bit. The only difference between this slant line and the volume, I mean, we're doing the same thing. However, there's a slant line. It's theta degrees on top of the horizontal line. Now, what if we transferred these properties? What if we consider this as our horizontal line, as our x-axis, and then we were to integrate? Wouldn't that just be a normal shell, not shell, sorry, disk method? Well, let's try. So, let's say we pick a point. We're going to do the same thing, slant line. We'll call this, let's say, f of x. And let's say we pick a point right there, and we get this tangent line at that point. And of course, let's say we have already our desired slant line, my bad, with this designated function mx plus b, because it can be anything. And we're interested in from a to b. Well, remember, in a way we want to transfer the properties, like if we were rotating around the traditional x-axis, for example, around here, we want to transfer these properties into here. So we're going to make like I guess I'll call it a transition. And because this curve is changing, it's not convenient to have analyze its properties at every point. So we pick a point so we can look at the tangent line, because in a way there's infinite amount of tangent lines, so if we can come up with a property, it'll start. So let's actually start. So let's say from here to here, because remember, we're transferring properties from different axes. So, okay. So, from here to here, this will be its change of x. In other words, I'll call it dv. And over here, I'll call it dx. Now, this is a very important property, because in typical integrals, remember that there's always a shell width or a disk width, and if you don't take into account the width, for example, right here, there's a certain amount of width right there, and in calculus this width is usually very insignificant, but it's very important, because if you don't take it into account, you won't get a volume. Well, in this case, this dv and this dx aren't similar. I mean, they are similar, but they're off by a certain proportion, and that's our job, to convert everything in dx mode into dv mode. Alright, so first let's see. At this point we have f of x, and this is the y mx plus b, and we want to find the distance from here to here, because remember, if this was our traditional x-axis, from here to here, we'll find the radius, and then we can just rotate, find the area, remember? So how can we find that? Well, let's assume we have theta degrees from the x-axis. Y equals mx plus b is theta degrees. I'll tell you what theta degrees is later on. So obviously this is going to be 90 degrees, and this is going to be 90 minus theta. And using geometry, that's 90 minus theta as well. This is 90 degrees. Alright, what would this be right here? Well, that should be theta, using geometry of course. And after this we have to stop, because we want to find what this length is. And we could find what this hypotenuse is. So, well, what is this hypotenuse length? This hypotenuse length is simply f of x, because that's the top part, right? Minus y equals mx plus b. Minus mx minus b. Right? So this represents the hypotenuse. So if we want to find this dark leg of the triangle, how would we do it? I would simply do the following. Sine of theta, because sine of theta, I'm sorry, 90 minus theta in this case, because it relates this opposite side and the hypotenuse, which is exactly what we need. So let's say I'll call that opposite, and I'll call that hypotenuse, right? So we want to isolate this opposite, so we'll move the opposite into the other side. Let's get another paper, and we'll continue. So we move hypotenuse to the other side. Hypotenuse sine 90 minus theta equals opposite. Alright. This opposite leg, it's exactly what we need. Now let's simplify this. What is the hypotenuse? Well, we figured out it's f of x minus x minus b. So let's go. That's f of x minus mx minus b. Okay, that's a hypotenuse. And then of course sine of 90 minus theta. That if that's not apparent to you, you should review your trigonometry. That's actually cosine theta equals opposite. Now, have you asked yourself, what is this theta? Because in a formula, having just theta is inconvenient, specifically when you're dealing with the revolution of functions. So, what is this theta? Well, let's actually look back. This slant line, y equals mx plus b, has a degree, but have you ever asked yourself, okay, we form a triangle right here. What is this theta? Well, don't we see right there m? M is a really important number because m represents slope. And what is slope? Delta y over delta x. Change of y over change of x. Well, in this case, don't you see that this part right here, this is the change of y between any point in the slant line, and this point right here is delta x. So delta y divided by delta x is we can actually put that as a trigonometric property. So let's actually go and exploit that. So right here we have so I pretty much drew a triangle. I wrote delta y, delta x, and there's a certain theta degree. Well, let me write tan of theta so we can relate both of these, delta y and delta x, equals delta y and delta x. My bad, delta x. And remember, delta y over delta x is simply m. So tan theta equals m. Now, how do we get rid of this tan theta? We just want to isolate the theta. Just take the arctan of both sides. That's theta equals arctan of m. So simply, theta is the arctan of m. Okay, now we can simplify our previous work that we had. We were right here. F of x minus b cosine theta. Well, theta, as we know, theta equals arctan of m. Now you might be asking yourself, well, how do we solve cosine of arctan of m? Well, using a simple trigonometric property, we can actually make a triangle relating arctan. For example, m1, and then we fill in the next part of the leg, the hypotenuse, and we get this relation. Now if you simply want to take the cosine, you just do adjacent over hypotenuse, which will be 1 over square root m squared plus 1. So now I can actually write that in there. So we get f of x minus mx minus b times 1 over square root m squared plus 1. This actually will equal our opposite, and it does a really good job at it. So what else are we missing? We already have this length. Well, remember, in a typical disk method, we needed the radius, right? And we needed the little width, the dx, in this case right there. So right now, this dx and this dv, my bad, should be infinitesimally small, something like this. But in purpose of analytical analysis, I'm going to actually extend it so we can look at its geometric properties. Alright, so we've already found the opposite, and now we need the dx and the dv. So how are we going to do this, and what are we going to do? So I want to relate this chunk right here, this dx, to this dv. How would I do that? Okay, so first I ask myself, this dx is just a line, just the length from this line to this line, right? So simply, this length right here is also dx, right? That forms a 90 degrees right there. But now, we want to relate it somehow to dv. Well, let's see. This is actually a hypotenuse. How can we find the length of the hypotenuse, or the degree at least? Well, if you notice, this tangent line that we formed right there, if we get a parallel line to the x-axis, we can actually see it forms I'll call it beta for now. There's a degree beta. Now, what is this degree? Well, remember, we just found the tangent line of the original f of x function. So, remember, if we have a function f of x, right, and we found this tangent line, I would write y equals mx plus b, like any other tangent line, but in this case, this m will be replaced with f prime of x at whatever x interval you're going to put it in. So we're left with y equals f prime x plus b. Now in this case you'll go on and solve for b, etc. But I'm only interested in the slope. Any tangent line, its slope is always the thing in front of the x, or the coefficient of x. In this case, f prime of x. So now we know what the slope is. And remember, the slope is simply delta y over delta x. And just like the previous example, this triangle right here has a degree beta. Alright? So tan of beta will equal this f prime of x. Because remember, f prime of x represents opposite over hypotenuse. Tan represents opposite over hypotenuse. How do we isolate this beta? Beta equals arctangent f prime of x. So in a similar fashion, it's just like the previous triangle we did. So now we know what this beta is. Let's actually write it in. So this is arctan f prime of x. Alright? And using trigonometry, using geometry rules, this degree should also be the same degree right here. That's beta, right here. Okay, so now we want to relate the degree, the leg dx, and the hypotenuse. I chose a hypotenuse because later on we're going to see how the dv is also connected to the hypotenuse. I didn't choose this leg because this leg has no relationship with how the dv is going to look like. So let's go on and continue this. So to find the hypotenuse, I will write this. Cosine of b, beta, which I have found already, equals this leg right here, dx, over the hypotenuse. Right? So, this beta we know as arctangent f prime of x, and we want to isolate, let's say, we want to isolate dx. Alright? So we're going to move the hypotenuse over here. Hypotenuse. And remember, our goal is to somehow find a relationship between dv and dx, and that's exactly what we're going to do, although it might not be apparent. So, cosine beta. Beta is simply arctan f prime of x. So we're going to have to take cosine of arctan of f prime of x. So we can just do a representative triangle right here. We'll put f prime of x right here. That's 1 because it's tangent, opposite over hypotenuse. We find the missing leg, or in this case the hypotenuse. And this is the degree. Let's say we want cosine, so we go 1 over square root f prime of x squared plus 1. So this simply equals 1 over square root f prime x squared, the f prime of x is squared, plus 1 times the hypotenuse equals dx. Alright, so we have two unknowns right here. Actually, we have the dx and we have the hypotenuse. Now remember, I chose hypotenuse because so far I think you can connect the hypotenuse to the dv. So let's actually go to it. So if I tilt it slightly, this looks almost like a rectangle, except here it's cut off. Let's finish the rectangle. So if I just draw it something like this, you see how this forms a rectangle, a complete rectangle. You see the rectangle right here? It might be a little bit crude, but this is pretty much a rectangle. And if this is a rectangle, this length from here to here must be the length from here to here. So this is dv. Alright? And we have to find a degree. How would we do that? Let's see. The only degree possible is this degree right there. Let's call it alpha. How would we find alpha? Okay. Well, let's think about this. Right here we have theta. Right here we have beta. How do we find that degree? Because we notice all the degrees right here. I'll use a pencil. From here to here are 90 degrees, except the theta. So if we can isolate what this degree right here is, we add it plus the beta and alpha. We can actually isolate but alpha. So let's actually go and continue that. So right here, let's go back. This is another 90-degree angle right here, and this is theta. So what would this be? That's simply going to be 90 minus theta. Okay, so we found the three angles and we want to isolate alpha. We know what 90 minus theta is and we know what beta is. Now we have to isolate alpha. So, get another piece of paper. We know that 90 minus theta, plus beta plus alpha, remember we don't know what alpha is, equals 90 degrees. If you still don't see it, ignore the theta. You have 90 minus theta, beta and alpha. You see how that's 90 degrees? It has to be because it's a rectangle. And now let's isolate this. If we 90 minus 90 will just cancel out, and then you're left with this. Let's see, 0 equals minus theta plus beta plus alpha. We want to isolate this alpha, so I'm going to move this thing right here. That's theta minus beta equals alpha. Alright, so we know what this alpha is now, which is really important because we know what the alpha is, we can actually exploit properties of this triangle, top triangle right there. So let's actually expand what theta and beta were. So if we look back, theta was simply arctangent of m. Beta was simply the arctangent of f prime of x. So this thing right here, that's arctan of m minus arctan f prime of x equals alpha. Alright, this is super important. Now we can actually continue with what we were doing. So let's look at this triangle now. We know what this leg is, and we know the degree now, and we actually define the hypotenuse. We want the hypotenuse because we related our other leg to the hypotenuse. So let's actually go. We related dx to the hypotenuse. Let's relate dv to the hypotenuse. Then we can cancel out hypotenuse, and we'll have a direct relationship between dv and dx. So let's go to it. If I draw the triangle right here, it looks something like this. 90 degrees right here. This is dv. This is alpha. And remember, if you want to find a relationship between this leg and hypotenuse, I'll simply write cosine alpha equals dv over hypotenuse. I want to isolate dv. Move hypotenuse. Cosine alpha equals dv. Now, what is cosine alpha? Well, remember, alpha simply equals arctan m minus arctan f prime of x. Alright, so we have hypotenuse equals arctan of m minus arctan f prime of x equals dv. Oh yeah, remember, I'm sorry, this is the degree of which we're going to take cosine. So now we're going to actually have to take the actual value of cosine arctangent minus arctangent f prime of x, and I'll stop there and continue the second video because I'm currently running out of battery. See you there.